Hey everyone, today we're diving into the AnimationTree state machine in Godot 4. If you've ever wondered how to keep your animations organized, a state machine is the answer. It basically acts as a brain that makes sure your character is only in one state at a time, like idling or running. I'm going to show you how to use your familiar if-else logic combined with the travel property to create super smooth transitions. It's a simple way to make your game feel professional without overcomplicating your code. Let's jump in and build it together. First things first. Let's go ahead and delete the animated sprite 2D node. That's because in this tutorial, we're going to use a regular sprite 2D node to set up our animations instead. Why use a sprite 2D? While animated sprite 2D is simple, a sprite 2D paired with an animation player gives you way more control. You can animate not just the frames, but also the position, rotation, and scale of your character all in one place. It's much more powerful for professional 2D games. Once the sprite 2D is set up, let's create an animation player. You might wonder why we need it if we're using an animation tree. Think of the animation player as the library where all your individual clips like idle or run are stored. The animation tree then acts as the brain that controls and blends those clips. You can't have the brain without the library, so the animation player is essential to make everything work. Now, I'm setting up the animations in the animation player. I'll enable the loop for idle, walk, and even the jump animation so they stay active as long as needed. However, I'm not looping the attack animation because an attack is a single action that should play once and stop. Setting these up correctly now ensures our state machine behaves exactly how we want. All right, Now that the animations are all set, it's time to create and set up the animation tree. Now, set the tree root to animation node SMATE. This lets us visually connect our animations. Also, remember to toggle active to on so we can see the animations working in the editor. First, we'll add the node and assign our animation player to it so the tree can access all the clips we just made. This is where we build the actual brain of our animation system. Now, add the animation nodes and connect them with transitions just like this. When setting up transitions, make sure to set the switch mode to immediate for all of them, except for the attack animation. This ensures our movements feel snappy and responsive. To make sure we can attack at any moment, we're going to create transitions to the attack state from every other animation. This allows the player to interrupt any action like running or jumping and trigger an attack immediately, making the combat feel much more fluid. For the transition from attack back to idle, make sure to set the switch mode to an end and the advance mode to auto. This ensures the attack animation plays fully and then automatically switches the player back to the idle state. Now, let's start the script. We only need one @onReady variable here. We'll create a variable called stateMachine and directly access the playback property from our animation tree. This single line gives us full control to switch between any animation state using the travel method. First, let's clean up our script by removing the old animated sprite 2D animation code. Instead, we'll use our new stateMachine variable to handle everything. By calling stateMachine.travel animation name, we can transition between states like idle, run, and jump much more efficiently. You might notice that when the player jumps onto a corner or edges of a platform, the attack animation triggers randomly. This happens because of unintended transition triggers. To fix this, we're going to disable the automatic transitions from other states and set the attack state to be handled fully manually. This way, the attack will only ever trigger when we explicitly call it in the code. Now, let's set up the attack animation. First, go to the input map in your project settings. Create a new action called attack, and assign an event to it, like a mouse click or a key press. This maps our physical input to the game action we'll call in our code. Now, let's write the code to trigger the attack. We'll add an if statement to check for our attack input. When the button is pressed, we'll command the state machine to travel to the attack state. Let's test it out and see the character strike. As you can see, even though I'm pressing the attack button, the animation isn't switching. This is because our physics process is constantly telling the state machine to travel to idle or run every single frame. Since those commands are firing so fast, they are overriding the attack command. To fix this, we need to add a condition to check if we are currently attacking before allowing other animations to play. First, I'm going to create a Boolean variable called isAttacking and set its initial value to false. We'll use this variable as a switch to let our script know whether the character is currently in the middle of an attack or not. Now, I'm updating the code so that as soon as the attack button is pressed, the isAttacking variable is set to true. Next, I'll use an if-else statement to manage the animations. If isAttacking is true, we'll only allow the attack animation to play. If it's false, the script will function as usual, playing the other animations based on our movement input. This logic perfectly prevents the movement states from overriding our attack. You've probably noticed that once you press attack, the animation keeps looping indefinitely. The reason is that we set isAttacking to true, but we haven't told the code when to set it back to false. Since the variable stays true, our if statement keeps the player locked in the attack state forever. As you can see, the attack animation wasn't triggering while the player was running or in any other state. This was due to the mouse input event we used earlier. To fix this and ensure the attack works smoothly during any movement, I'm switching the input event to the right shift key. Now the keyboard will handle both movement and combat, preventing any input conflicts. And there you have it. As you can see, the character now moves and attacks seamlessly, regardless of its current state. While this is a basic setup, mastering this logic is crucial before moving on to advanced systems like hierarchical state machines or behavior trees. Experiment with these nodes, try adding a jump or slide state on your own, and see how the transitions behave. In our upcoming videos, we'll explore how to make these systems even more robust and scalable for larger projects. Don't forget to like and subscribe if this helped you out. Happy developing, and I'll see you in the next one.